Coming up on Catalyst, answering the big question in climate science. What happened to global warming? Illustris, the computer simulation that reveals the life of the universe. And green alloys, reincarnating products deemed unrecyclable.
"17 years ago, a warm wind was blowing across the Pacific. As it blew, it pushed sun-warmed waters westward, piling them high to the northeast of Australia. When the winds eased, the warm waters washed back across the vast ocean, releasing masses of heat to the atmosphere in what became the mother of all El Niño events.
The Florida storms are being blamed on El Niño.
Wild storms and heavy rain in South America.
A man-made permanent drought.
It was 1998, and the climate seemed set on a frightening trajectory.
What the world is experiencing could be part of a climate shift.
In a few years or a decade or so, we'll go into a permanent El Niño.
But the years that followed didn't live up to predictions, leading to a crisis of confidence.
They have been deliberately exaggerating the evidence, overstating the case, frightening people, frightening even children.
The globally average surface temperature hasn't increased in any significant way since 1998.
In fact, it can be argued since 2003 it has cooled off somewhat.
It became the most important question to answer in climate science today. What happened to global warming? It's a cold and blustery day in Boulder, Colorado. It seems a fitting start to a story on what's become known as the global warming pause. It's a well-established fact that people are less likely to believe the world is warming when there's cold weather about. But it was also here at the National Centre for Atmospheric Research that a distinguished senior scientist found himself at the centre of a climate conspiracy storm.
This related to what was subsequently called ClimateGate, in which a whole bunch of emails were stolen.
Among the many hacked emails in the 2009 ClimateGate scandal was one from Dr. Kevin Trenberth to a colleague. Skeptics seized on one particular sentence as written proof that climate scientists were involved in a large-scale cover-up.
It was picked up as me saying that there was no global warming, somehow or the other, and completely misinterpreted, and it just propagated all over the place. It was amazing to see.
Yet, the world didn't seem to be warming. At least not much. While the period from 1975 to 1998 had seen a rapid rise of global average air surface temperatures, in the years since, the rate of rise has slowed dramatically, leading a vocal minority to question predictions of catastrophe.
So we're getting this growing divergence between the observations and the climate model simulations.
You have at least to consider the possibility that the models are not reliable for one reason or another.
On one point, the skeptics were right. None of the models used in future climate projections predicted the hiatus. And while the slowdown for the first few years was written off as natural variability, lately it's become something to explain. From the data he's been analysing, Dr. Trenberth sees a planet heating up just as fast as ever.
We can look at the energy budget of the Earth by looking at information from satellites that are flying above the atmosphere, which actually track the incoming solar radiation from the sun, how much is reflected, and how much the Earth is radiating back to space. It's not absolutely accurate, but it does track the year-to-year variations very well.
His calculations show our budget is continually in surplus. More energy coming in than leaving the atmosphere.
Given that there's an energy imbalance, Where does that energy go? How much has gone into the oceans? How much has gone into melting Arctic sea ice, warming the atmosphere, warming up the land, changing evaporation, and therefore changing clouds, which can also change the brightness of the planet. And when we first did this, there was some quite substantial discrepancies, that in some years we can't account for where the energy has gone.
And that was the cause of the frustration expressed in Kevin's email. Monitoring systems simply aren't sophisticated enough to track all of the heat exchanges on the planet. The main focus in global warming has been air temperatures because it's the easiest to measure and it's the temperature we feel. But it's a tiny fraction of the planet's total heat content, and it's also highly variable. As greenhouse gas emissions have risen over the last century, the long-term trend in air temperatures is obvious. But zoom in on the chart and you'll see fluctuations. These swings are put down to natural variability. The current hiatus is no different. But this time, climate scientists have been under pressure to pin down the exact cause. There have been several.
So the sun went into a relatively quiet phase. In addition, there have been a number of small volcanoes that put debris into the stratosphere that blocked the sun. And what about the air pollution? China has been developing enormously. What has that done?
In total, aerosols and solar activity are thought to account for about 20% of the pores. But the biggest contender for where the rest of the heat is going is the one that's hardest to measure. The oceans absorb a whopping 93% of the world's excess heat.
I've been working with the European Centre for Medium Range Weather Forecasts, and they have developed an ocean monitoring system that synthesizes all of the information. Sea level measurements, the measurements from the floats, sensors that are measuring sea surface temperature, and so on. And what we found is that after about 1999, a lot more heat is going deeper into the ocean. And this is unprecedented. Is this just a consequence of the change in the observing system, or is it real? And I think we have good reason to believe that at least some of this is real.
Multiple lines of evidence converge here in the Pacific, the largest and deepest ocean in the world.
If you rotate the globe around, that's all you see for part of this hemisphere is just a big fat piece of ocean. The Pacific Ocean is huge influence on climate.
Professor Matthew England has been key to nailing down how the Pacific has been dragging down world average temperatures.
We had to look for something about the climate system post-2000 that was dramatically different to the climate system in the 80s and 90s. And one of the most dramatic things you see in the system is this flip in the Pacific Ocean. If ever you travel to the tropics in the Pacific Ocean, there's a prevailing wind from the east towards the west. And these easterly winds push a lot of the surface water across the West Pacific Ocean. If they remain for long enough, this water starts to get subducted into the ocean interior. During the 80s and 90s, the winds were quite weak. Not a lot of heat was getting subducted into the Pacific Ocean during that time, and a lot of heat was remaining in the atmosphere.
Then came the massive El Niño event 17 years ago.
In 1997-98, there was a tremendous amount of heat that came out of the ocean, and we can measure it. And so the ocean actually cooled quite substantially. And so we think that this may have then kicked the whole behavior of the Pacific Ocean into a different mode.
The ocean once more began to build up heat. The change in the way the ocean either releases or draws in heat is part of a regular long-term cycle called the Pacific Decadal Oscillation. Each phase lasts around 15 to 30 years. When Dr. Jerry Meal from Boulder studied climate models with hiatuses, he discovered they linked closely with the negative phase of this pattern.
And sure enough, the extra heat was going into the deeper ocean. So that was kind of the first tie we had, a tangible link to where the heat was going during these hiatus periods. And this connected then to stronger trade winds.
It was Matthew England who found these winds were unprecedented in strength this century.
The winds are that much stronger than we'd ever seen before in the observations.
The winds are in fact being turbocharged by abnormally warm waters in the Atlantic. As air races from high pressure to low, the winds push the warm surface waters west.
So over the last 20 or so years, the sea level over the West Pacific has risen quite dramatically above the global average sea level rise, whilst in the East Pacific it's declined.
And in this case, it's been piled up to such an extent that there's been a 20 centimeter rise in sea level compared with the Eastern Pacific. And that, to me, seems like a very large number.
It sort of reaches a breaking point, perhaps, where that heat then sloshes back to the East Pacific.
And that then adds to the warming from the increasing greenhouse gases, and you get real sudden increases of temperatures globally. The last time that happened was in the mid-1970s. Global temperatures warmed almost a half a degree centigrade, which is almost half of the warming we got in the whole 20th century.
What that means is we're currently in the phase before the next global temperature jump.
There'll be warming out of this hiatus at some point in time, whether it's this year or in 5 years' time. There's going to be warming, and unfortunately what we're seeing in the models is that the warming out of the hiatus is going to be rapid regardless of when that hiatus ends.
But a small minority of scientists disagree.
That's where I break with my colleagues. I just think there's a lot more uncertainty. We're now in the cool phase of the Pacific Decadal Oscillation, and I think that is the major thing that's causing the pause. And my understanding of the Pacific Decadal Oscillation is that we could stay in the cool phase for another 2 decades. So where does that leave us in terms of thinking that this sensitivity that we've deduced, largely based on this warming in the last quarter of the 20th century, during that period we were in the warm phase of the Pacific Decadal Oscillation.
And this is a thought which is, for about 30 years, people have tried to ignore because it takes away from the thought that most of the rise in temperature is due to increasing carbon dioxide in the atmosphere.
Look, I agree that the warming in the 80s and 90s certainly would have had a component of Pacific natural variability to it, but it was beyond just that. So if you think about the natural system without greenhouse gases, it would see cooling of the atmosphere globally, then warming in the positive phase, and we'd be flatlining over 100 years. We don't see that. We're seeing hiatus decades.
And there is one other possibility, that there is no missing heat. Changes in ocean circulation have changed the pattern of the clouds, which is reflecting more solar radiation, and so the Earth isn't heating as much. So unfortunately, the observations aren't quite good enough to distinguish between those two ideas.
There's no evidence that clouds can account for this hiatus. Many things have occurred over the last 15 years that should have given us one of the coolest decades over the last 100 years. It's actually the warmest on record.
We've seen that in Australia, we've seen that in the United States. All kinds of thousands of temperature records were broken.
A lot of the continental regions have continued to warm up, and we've seen an increase in, for example, heat extremes over a lot of continental areas, all the while that the global average temperatures haven't been doing much.
Arctic sea ice has declined dramatically, way beyond the projections. Sea level is rising faster than we projected even just 5 or 10 years ago.
All things considered, there's been no global warming pause.
The whole of the climate system is really warming, it's just that the warming can be manifested in different ways.
For some people it's very easy for them to get this, but there are other people who are just absolutely obsessed with derailing the basic physics of climate change, and for them this poses a great little story that global warming's paused. I wish they were right, but unfortunately they're wrong.
In the beginning was the Big Bang. From that came everything. Galaxies, stars, planets, you and me. But how did it all happen? Wouldn't it be wonderful if you could just kick back and watch a movie of the life of the universe and actually see how everything unfolded? Well, thanks to a new scientifically accurate computer simulation, you kind of can. This is the Illustris program, the most advanced computer model of the universe. On a supercomputer, it took 3 months to run. That's equivalent to more than 2,000 years on your home computer. It was created by a large international team of astrophysicists. One of them was Boston's Paul Torrey.
The Illustris simulation is our attempt to simulate a slice of the universe from soon after the Big Bang until the present day.
The program's made its mark around the world, including here in Melbourne. How impressive is this simulation?
I think, as you can see, it's incredibly impressive, and seeing really is believing.
The Illustris simulation is really getting a lot of detail there that wasn't present in previous simulations.
And it not only gets the detail, it models a huge chunk of the universe, a cube 350 million light years across, that encompasses tens of thousands of galaxies. To appreciate why the simulation is so good, you first need to know a little about our universe's majestic inhabitants, galaxies. They're so beautiful, I put one on the lounge wall. This is the Sombrero Galaxy. Stunning, isn't it? But imagine it as an impressionist painting made up of billions of little dots. Well, each one of those dots is a star. There are about 100 billion stars in a typical galaxy, and there are many billions of galaxies in the observable universe. Space is really, really big. Our star, the Sun, is in the Milky Way.
The Milky Way is a spiral galaxy that actually is a fairly common galaxy within the local universe. We think that about 70% of local galaxies are star-forming disks that have spiral arms of some sort.
Star forming is one of the key jobs of a spiral galaxy. It's currently happening in our Orion Nebula. This is an enlarged image of it taken by the Hubble telescope. It's a pretty amazing facility.
It is. You get to walk inside the Orion Nebula and see it in Hubble detail.
And I can see a little black smudge over there. What's that?
So that black splodge is a solar system being born, a new star being formed, and a disk of dust and gas that's going to collapse and form planets.
While our galaxy is a spiral, the other major type is elliptical.
Elliptical galaxies are the largest galaxies in the universe. These galaxies are sort of football-shaped or soccer ball-shaped, and they don't really have much star formation within them.
So why do galaxies come in these two very different varieties? To find out brings us back to the Illustris simulation. It begins just a few tens of millions of years after the Big Bang. There were no stars or galaxies then, just a universe filled with gas made of ordinary matter and dark matter.
Dark matter is invisible. It doesn't interact with light, so we can't see it.
There's lots of it. It holds galaxies together, but exactly what it is, what kind of particle it is, still remains a mystery.
But it does have gravity. In the early universe, Illustris depicts dark matter as blue, and gravity causes it to gradually clump together, forming a vast scaffold for the ordinary matter galaxies to form around. It's in the high-density spots the first galaxies appear. Zoom into one and you see why Illustris is so impressive. Incredible detail has been modelled, and realistic-looking galaxies have been produced.
Here we're zooming in on one galaxy which actually happens to have a lot of properties similar to our own Milky Way galaxy. We see that it has blue star-forming arms, and then it has an overall disk-like structure.
And remarkably, Illustris also produces the other kind of galaxies, the ellipticals.
I think the most novel aspect of the simulation is the formation of both disk-like systems and elliptical systems side by side. That had been really hard to do in the past.
Elliptical galaxies form from spirals.
This is when two massive galaxies collide together and they just essentially cause a train wreck, a gravitational train wreck, where all of the nice structures, spirals, everything like that is just obliterated, and we find this slightly elongated structure forming essentially an elliptical blob of light on the sky, hence the name.
And to make things personal, racing towards us right now is the spiral Andromeda Galaxy. It's travelling at 120 kilometres per second.
It really is a Jaws moment. It's going to take a few billion years, but there's a bit of a collision coming.
When Andromeda collides with us, it could look a bit like this.
What happens is that two galaxies first come close to one another. They go by for one first passage, and that's a very strong interaction that they have there.
They're going to swing back towards each other and slosh around a little bit.
Remarkably, while the galaxy's structure changes completely, none of the billions of stars in either galaxy is likely to hit another because there's so much space between the stars.
So when the two galaxies collide, the stars will actually pass by each other, and there'll be very few collisions between the stars.
It's unlikely that the Sun or even the Earth will be disturbed by this merger. Eventually, the stars come together and mix in such a way that, in fact, we can't distinguish the two galaxies from one another.
At that point, our spiral Milky Way will have become an elliptical. To see another example of Illustrious' realism, wind time forward to about 5 billion years after the Big Bang. These bubbles are enormous outpourings of energy that spread matter from galaxy to galaxy. They come from supermassive black holes.
Almost every large galaxy has a supermassive black hole. Our galaxy has a black hole that weighs millions of times the mass of the Sun, and there's black holes out there that weigh 1 billion times the mass of our own Sun.
When some unsuspecting matter falls into one of these black holes, huge jets of energy shoot out. Illustrious actually allows us to visualise these gigantic bubbles spreading through the cosmos. Now, while the realistic details Illustrious produces are pretty impressive, perhaps the most convincing demonstration of its realism is a single picture. The Hubble Space Telescope took this picture of deep space several years ago. Those tiny splodges are entire galaxies.
The code should have a step.
Paul's team put a mock Hubble in their simulation and took a virtual picture in their virtual universe.
We gave our mock Hubble Space Telescope the same camera, the same lens size, and the same filters, so that the image should be really analogous to what's actually seen in the real Hubble Space Telescope image.
On the left is the real Hubble image. On the right is the one from the mock Hubble. The two were extraordinarily similar. Illustrious shows we do now understand the basics of how our universe evolved. If you'd like to look at the full Illustrious simulation, go to our website.
Our landfill space is rapidly reaching a tipping point. Some of this waste can be recycled, but the more complex the product, the more difficult it is to break down. Car windscreen glass, CDs, and expensive bike parts are just some of the products deemed unrecyclable. Engineers and material scientists at UNSW are turning these unrecyclables into new green alloys for industrial use. An alloy is a mixture of elements. A parent metal, like iron, is combined with another element, such as carbon, to give it superior strength and hardness. This makes them perfect for making industrial tools like drills, diggers, and cast iron pipes.
We want to reform our waste so that ultimately it's not seen as a plastic or a glass, but it's actually seen as a resource of elements. So in plastics, we've got carbon, in glass, we've got silicon.
So it's like reincarnating?
Well, actually, it is a reincarnation of the product.
And to encourage local industries to recycle, Professor Veena Sahajwala sourced bike parts from David Musgrove.
quite ironic that bicycles are considered an eco-friendly form of transport, but actually some of the high-end bikes are made of carbon fibre and they're currently not recyclable.
Hi, Dana. Hey, how are you?
Yeah,
I'm
good,
going to hand
you.
this to you. Good to see you
Yeah, good
again.
to see you again, for sure.
So you've got some samples for us, huh?
Yeah, I do.
Yeah, that's good. That's good. What have you got for us this time?
So carbon fibre frame once again.
Yeah. Thank you so much.
But also, I've got you a bunch of CDs
Oh,
that
you
you've
do?
talked about.
Yeah, fantastic.
The aim is to recycle the carbon from the CD or bike part and combine it with the parent metal, iron, to form an iron-carbon alloy. The iron sits on top of a tiny piece of bike part. It's inserted into the furnace and heated to 1550 degrees Celsius. At this temperature, the carbon atoms from the bike part transform from a complex solid structure to highly ordered crystalline carbon. This gives the carbon a better chance of reacting with the iron.
So there's the interface between the solid carbon and the liquid metal. The carbon atoms from this composite are actually dissolving into liquid metal, and you're then converting iron and making it into an iron-carbon alloy.
They have found that this process is faster and is therefore more efficient than using coal, the traditional source of carbon. This is because coal retains its disordered carbon structure even when heated and is slower to react with liquid iron. But the key point here is that they're transforming waste materials.
What we're really trying to do here is look at the process by which we arrive at the end product by using waste resources as our raw materials.
They're also testing silicon-based products like car windscreens.
We actually have a pellet that contains waste windscreen glass and plastics mixed together. We want the silicon to come out of that glass because we want the alloy to contain silicon, and we can start to see these shiny droplets. And of course, that's your reaction product. And ultimately, the goal here is transforming the waste windscreen glass and the plastic into a green alloy that contains silicon and carbon. The icing on the cake for me really is about the fact that you can actually take end-of-life resources, free up those elements that were present as plastics and glass, and convert them into completely different end products like the iron-based alloys. You've transformed it and given it a whole new life.
But the real test is whether this research can be taken from the lab into the factory.
So yes, it's absolutely possible to take the findings in the lab, work in partnership with industry, and apply that new knowledge out into industrial processes.
We consider it extremely important to reduce the carbon footprint, and we have already produced a number of small castings in our laboratory. If the material is suitable for use in the casting, if it's cost effective, we'll certainly be very interested in putting such a product into production.
It gives people a whole range of new ways in which to transform those waste materials that we've been putting away into landfill and creating new value-added materials. So good for the environment, good for the economy.
Next time on Catalyst, we travel to Tokyo. How does a city of rivers defend itself in a land of flooding rain? Crying, are tears of joy different from tears of sorrow? And how the open plan office can affect your health. Connect with Catalyst on Facebook, Twitter, Instagram, YouTube and our website.